I'm today's PhD speaker. I'll be talking about sargassum in the tropical Atlantic, from tipping points to sustained inundations. As you can see in the photos across the top, sargassum can be very beautiful, and in addition to that, very beneficial by providing habitat for various marine creatures. And when it's out in the blue water areas of the ocean in particular, it's home basically in the Sargasso Sea, which was named after it. It can be a very good thing. But along the bottom, you can see photographs of a new phenomenon that began occurring down in the Caribbean and also the shores of Africa in 2011. And when sargassum comes ashore, it's down now in the tropical Atlantic. We'll get into that. That's one of the main points, how that happened of this talk. But it can be quite a nuisance, piling up on tourist beaches where it bakes in the sun and it begins to smell and have bugs, and the tourists don't like it. And also it's harmful for wildlife, especially turtles that are trying to nest, and then their newly hatched baby turtles need to get across this barrier somehow. It also makes it difficult for fishermen to access their boats and do their normal activities. And so it can be a good thing in the right place, but then mysteriously in 2011, as I said, it began appearing in the tropical Atlantic and has been causing trouble ever since. Next slide, please. Yes, this talk is based loosely upon a recent paper that a number of us wrote. It took a whole village to write this paper with all kinds of different interdisciplinary expertise. It came out in Progress in Oceanography in January 2020, and the citation, the reference to find it is down below, called The Establishment of a Pelagic Sargassum Population in the Tropical Atlantic, Biological Consequences of a Basin-Scale Long-Distance Dispersal Event. And because everybody was so important in this work, I'm going to name all these names: Rick Lumpkin, Nathan Putman, Ryan Smith, Frank Mueller-Karger, Digna Rueda-Roa, Xuanmin Hu, Mengqiu Wang, Maureen Brooks, Lou Gramer, and Cisco Warner. And it took each one of these individuals to get this thing accomplished. Next slide, please. Okay, the outline we'll talk a little bit about, just briefly, an overview of how did the sargassum get into the tropical Atlantic, the Sargasso Sea and the tropical Atlantic winds and currents.
May I interrupt you for a second? I'm still seeing the first slide. I don't know what to do about that.
I'm seeing the outline slide. I saw all three of them. Renelis is showing the presentation.
I don't know what to do.
I see the outline. It must just be you. Is everybody else seeing outline right now?
Yes, I am.
Okay, thank you. Claudia, I think that's you. Is that you, Claudia?
Yeah, that was me. I don't know what to do with now.
Okay, well, just listen. It'll be like a story. The role of the North Atlantic Oscillation, the case for a long-distance dispersal, drifter data and windage comes into play in the story, and then model simulations. And then finally, new sustained growth in the tropics and recurring seasonal inundations in the Caribbean. We'll get into coastal nutrient sources, equatorial mixed layer dynamics in the ITCZ, and seasonal and interannual variability. And then at the end, we'll have a brief mention of the conclusions and future work. Next slide. All right, so now that you get the kind of background of the whole thing, what triggered the first sargassum event in the tropical Atlantic in 2011? Let's see, I have to move my chat window over a little bit for that. Our hypothesis is that a large-scale wind anomaly triggered a long-distance dispersal event that transferred sargassum from the Sargasso Sea into the eastern Atlantic. To back up for a moment, prior to doing this project, there were several papers that came out soon after 2011, all of which felt as if they had shown that the sargassum could not have come from the obvious place, the Sargasso Sea, because the data just didn't support that using drogued drifters and other data sources. We'll see what caused this discrepancy when we get into that part. Anyway, changes in the winds over the North Atlantic strengthened and shifted the westerlies southward, caused by the extreme negative North Atlantic oscillation during winter 2009-2010. The anomalous eastward winds and currents defined a new but temporary pathway for Sargassum to move eastward out of the Sargasso Sea toward Gibraltar, where it joined the southward flowing Canary Current along the coast of West Africa. From there, the Sargassum was able to disperse south and southwest into the entire tropical Atlantic and Caribbean Sea, where it flourished under the favorable light and nutrient conditions that it found there. So that's the whole story, and now we'll go ahead and show you how we got there. Next slide. All right, this is just a little sort of visual of the main event. The wind anomalously blew Sargassum under the effective windage along the northern side of the subtropical gyre in Sargasso Sea. It blew it farther over towards Gibraltar than usual. And then this is just a surface drifter. We used those to help show ourselves what pathways it took. Then it traveled down south along the coast of West Africa, down into the tropics, under the influence of the ITCZ, which moves north and south seasonally. And when it got over into the area of the Caribbean, starting, as you can see, this picture is from Wang et al., 2019. Beginning in 2011, it started showing up where it had never been really seen before, and it has increased in magnitude. This plot goes through 2018, and it's even more so now, recent data and inundations down in the Caribbean, and as we shall see, other areas as well. So this is the sort of graphic novel, one-page version of the whole story. Next slide. All right, to brief, I don't think most of this audience needs to be briefed on the physical setting. This is the prevailing winds in the ITCZ. The ITCZ is the portion shaded in yellow and stippled. We have mostly the setup is the westerlies to the north of the North Atlantic, and the trades. The westerlies are going to the northeast, and the trades, of course, are blowing to the southwest. And this is January and July. And the biggest change in the two seasons is the location of the ITCZ, which kind of, as you can see, the trade winds are kind of sliding north-south a little bit, and I guess I'm pointing with my finger at my screen. You can't see that, but you just have to do it yourself. But and the southeast trades are slightly different too. It's all mostly a north-south shift. Next slide. And the currents, the surface currents, you've seen this, the very simple picture of the Sargasso Sea in the left and the green map there. Usually, because of the setup of the subtropical gyre, it's a convergent area, and things such as Sargassum and marine debris are sort of trapped in it and don't get out unless there's an occurrence, as we've mentioned, that causes a temporary escape route out of the Sargasso Sea. So over here, you just see a beautiful, I believe this is from 1943, depiction of the Atlantic currents, and it's actually quite accurate according to what we know now. It has many features, such as where the Canary Current splits in one branch becomes the North Equatorial Current. The other branch goes down south around the coast of Africa, becoming the Guinea Current. And then, oh, thank you for moving that little cursor. And then we have the east-west system of tropical Atlantic currents. The Caribbean Current flows into the Gulf of Mexico's Loop Current, into the Gulf Stream, and closes the gyre. So that's the big picture of the setup. We don't need to worry about the northern currents. So next slide. All right, the North Atlantic Oscillation is very important to this story also, because it is what provided the wind anomaly that may have opened up that temporary escape route for the Sargassum, as I hope I'll be able to show you. The NAO is a periodic change in atmospheric pressure between Iceland and Portugal that affects the strength of prevailing winds, the westerlies, over the North Atlantic Ocean. Here's a sort of a cartoon map of the positive phase and the negative phase. The positive phase is a more intense difference in pressure between the northern and southern part, and the negative phase is a less intense. And you can see that the westerlies have moved to the south, just as we were referring to that and pointed more straight towards Gibraltar than they are in the case of a positive phase. Over on the right, we see two time series of the North Atlantic Oscillation Index. You can see that in the annual average, let's see, it's hidden slightly underneath my GoToMeeting chat room, but you can see that 2010, if you can see the full screen, it's the biggest negative, the most intense negative event in the NAO that there has been in this entire record since before 1900 to the present time. And in the lower right, it's the monthly average, and you can see that one of the reasons 2010 was so extreme is that it had its larger, more prolonged event at the beginning of 2010, actually December 2009 to March 2010, and it had a recurrence, which is something that happens fairly often with the NAO at the end of the year. That happens because the first one preconditioned and had very cold water underneath. And then it gets capped off by warmer surface waters, and however, it's waiting there just underneath that surface layer to bring up more of the event. So anyway, 2010 is what we're going to focus on. There was also another event in March 2013 that may have contributed, but for today, we're going to talk mostly about the first negative event in 2010. Next slide. All right, the wind fields during and climatologically and during the event, I computed from the NCEP reanalysis climatological winds. And in the upper panel, you can see it's the average of 2008 to 2015 in January, February, March. This is the normal setup. You can see that the westerlies, the Sargasso Sea nominally is located where the oval is. And this other rectangular box is where I've done some averaging of certain properties. Later, you'll be able to recognize that box. Anyway, the westerlies are strongest well north of the Sargasso Sea and the rectangular box. And the trade winds are quite strong, and the winds offshore of Gibraltar are to the south. In the lower panel, we have what happened during the negative NAO event. You can see that the westerlies have strengthened. Reds are stronger in meters per second, and you can see that they've shifted to the south into the box, and that the winds are now blowing directly towards the Mediterranean through Gibraltar, and also that the trade winds have shifted south somewhat and weakened. And then just down here, you can see the ITCZ location. Next slide, please. All right, well, taking a closer look also from the NCEP reanalysis data. Now this is averaged over that rectangle that I pointed out in the last slide. These are the eastward NCEP winds. The climatology is shown in red, the monthly climatology. The actual monthly winds are shown in blue, and in the lower plot, the anomaly of the winds over the climatology is shown in green with a different scale on the y-axis. Note the reversal of the normally westward winds during the negative NAO periods in early 2010, late 2010, and March 2013. It's really quite an amazing anomaly, all caused by the NAO, in which it not only affects the magnitude of the winds, but actually changes the direction of them in this box. So this is quite important to the story. Next slide. All right, and what does this do to the currents? Well, it's the surface currents are very much affected by the winds, as we will demonstrate. These are the climatological surface currents as defined by January, February, March 2008 to 2015 in the upper panel. Much as we all know about is kind of the doldrums in the middle of the Sargasso Sea and the subtropical gyre going anticyclonic looping around it. Things tend to be retained, drifters, sargassum, marine debris inside that gyre. And then we can recognize a few other features such as the North Brazil current flowing into the Caribbean current, loop current, etc. This is the normal setup. And down below we have during January, February, March 2010, during the NAO anomaly, we can see what happened to the currents. these are just the straight on surface currents from the model now with no windage or anything. We'll get into that in a moment. You can see, of course, just like with the wind field, that the lowest currents have shifted to the southern edge of the rectangle, and otherwise the gyre seems to have shifted also. Well, it's southward and flowing into the Canary Current. But I'll have more to say about this when I get to the next couple of figures. Next slide. All right, now we're going to look at some surface drifter data. You are very well aware that the surface drifter program, the Global Drifter Program, is Rick Lumpkin's project, one of them, and that it's run out of the data run out of AOML and PHOD. This is a picture of a drifter with a surface float that speaks to that communicates with a satellite, an antenna on it, and a drogue, which is somewhat like a sea anchor or something that's centered at 15 meters depth. And the interesting thing about these drifters is that although they're supposed to be drogues so that they track the upper layer of the surface currents, sometimes, quite often, the drogues come off eventually. And then what you get is a measure of this very surface velocity and patterns of circulation without the drogue. So when you divide them up into drogued and undrogued, you get some very interesting results that start coming out. First of all, the mean speed of drogued drifters is in the upper right plot, and it basically has all the features you might be recognizing from what you know and from what we've already shown, the subtropical gyre, the east-west stronger currents of the tropical Atlantic. But when you compare it to the mean speed in the lower right of undrogued drifters, you can see that undrogued drifters, which are more subject to surface windage, have a much stronger gyre in both the North Atlantic and the South Atlantic, and in particular, the big wide flow of the south side of the North Atlantic subtropical gyre is quite a bit stronger, as is the southward flow along the coast of Africa. And this will become important to understand if you now start to think that perhaps Sargassum would behave like an undrogued drifter, then it becomes important to examine what the difference is between drogued and undrogued. So the next slide is very interesting. This was an exciting result to see for the first time. This is showing pathways into the Caribbean from the drifter data. The upper panel shows results from drogued drifters and the lower panel from undrogued drifters. Previous studies found that the Sargassum in the tropical Atlantic could not have come from the Sargasso Sea because these studies relied only on the drogued drifter data. But the undrogued drifter data reveals that there are two distinct pathways into the Caribbean. In other words, the drogued drifters all come from the tropical Atlantic and presumably from the South Atlantic at some point. The black means the percentage is 100% of the drogued drifters. We started them in the Caribbean, and they had to go there. And then we looked at what is the percentage of the fraction of them that came from various areas. And so in the lower undrogued drifter map, you see two distinct pathways, one from the north and one from the south. And the NAO wind event that moved Sargassum over to the far northeastern Atlantic allowed it to follow the northern path. It's important to notice that this northern path is always there, but its source is to the north of the Sargasso Sea. But during the wind event, the Sargassum was able to move over so that it could catch this other route into the Caribbean, which it had never done before. So windage is likely to influence Sargassum similarly to undrogued drifters. And recent empirical studies have been able to confirm this by Putman et al. And Olasquaga et al. 2019 and 2020. Windage provides a 1 to 3% of the wind speed boost to the surface currents. And so once you add that bit of windage, or you're an undrogued drifter, you find that a pathway opens up from the north into the Caribbean. Next slide. All right, I'm going to have to go briefly through the windage thing. Several of these topics in this paper could be the subject of whole seminars on their on their own, but I'm just going to give you an overview of this. The role of windage. Windage is the additional wind-induced drift of material floating at the free surface, resulting from direct wind forcing on the sea surface, as well as on floating or partially submerged objects. As you can see, sargassum, turtles swimming through it, and an indication, if you would like to have this PowerPoint later, the references that some of these things are drawn from are in the small font underneath the figures. Next slide. These upper ocean wind force processes, we and others consider them all as a sum, and we parameterize it by the 1 to 3%. But there are actual physical processes that are fairly well understood that contribute to it. Surface wind stress, turbulent kinetic energy flux, in other words, breaking waves, Stokes drift, and Langmuir cells and rows, which cause an interesting visual pattern, as you can see the sargassum lining up on the sea surface there. This happens quite often. Fishermen see it all the time out here. Next slide. Large-scale numerical models of ocean circulation do not resolve many of the processes in the ocean's near-surface layers. Floating objects tend to move downwind at a speed proportional to, but much smaller than the speed of the wind. As I said, generally 1 to 3% of the wind speed. The exact percentage depends on the physical characteristics of the floating object, how much of it is submerged, and the magnitude of the wind speed. Next slide. In our study, in our Progress in Oceanography paper, the effective surface velocity was represented as the sum of the velocity from, in this case, the NCEP reanalysis data, and the wind speed, the wind velocity at 10 meters above the ocean's surface, modulated by the windage coefficient, which I said is in the 1 to 3% range. And for the purposes of these calculations, we took a conservative 1%, which turned out in the empirical studies that have been done, very few, but it has shown that 1% is a very, very good estimate for the movement of sargassum, actual sargassum itself at the sea surface. So now these are the currents with 1% windage added. So according to the methods being used here, this is what we consider the actual surface velocity and movement of sargassum would be like. You can see that in the climatological picture, in the top row, top plot, you can see that the flow, although it is southward off Gibraltar, it is originating north of the rectangle there. It's coming from the North Atlantic, and then feeding the north equatorial current. And there's very little direct flow down around the West African curvature into the tropics there. However, in the lower panel, during the anomaly, you can see that the southward shift of the westerlies caused the flow to go directly over to Gibraltar and even into the Mediterranean Sea. It actually caused a sea level rise that was measurable in the Mediterranean, and Dennis has written a paper having to do with that. And it also caused a very strange phenomenon in which it blew a bunch of Portuguese men of war that are usually in the Eastern Atlantic into the Med for the first noted time that has happened, and it caused great problems that summer during the tourist beach season. There were papers on this too, quite interesting. But anyway, so you can see that the flow went farther, it escaped, in other words, the Sargasso Sea, and then joined the Canary Current, the flow pattern, and you can see that some of it then curves over towards the Caribbean, while another portion of it rounds the curvature of Africa and joins the tropical circulation, where it basically things down there, drifters, apparently sargassum, sort of flow back and forth with the equatorial current system and the North Brazil current, and the seasonally varying retroflexion of that current, and in the spring into summer, the direct flow into the Caribbean. So next slide, please. Now for an entirely different look from entirely independent data, We also, Nathan Putman was the lead on this part of it, used the HICOM backtracking model to get some very interesting results also. Now in the upper panel, we see the location of particles released. This is backtracking. So the particles were released in the Caribbean at random locations and at a 5-day intervals throughout the Caribbean, backtracked for 6 months, the black dots. In other words, if a particle was in the Caribbean in the spring in 2011 when the Sargassum was there, where did it come from? 6 months before, 1 year before, the blue dots, and 2 years before, the red dots. As you can see, much like the drifter picture of the undrogued drifters, these HICOM particles came from both the North and the South Atlantic, and specifically most of them along the eastern side of the Atlantic. The dashed line indicates latitude 23 north, the southern boundary of North Atlantic origin. And note that these HICOM surface currents include a 1% windage factor at the surface in order to best simulate Sargassum. Now in the lower panel, these are trajectories, not just dots, of only those particles backtracked from the Caribbean Sea to the North Atlantic, north of 23 north. So we've eliminated all the ones that did not originate north of there. Within 1 year blue or 2 years red, the tracks indicate 2 primary routes based on the transport duration. A shorter western route through the Greater Antilles, which impacted the northeastern Caribbean. A reminder, these are blue and they take 1 year. And a longer eastern route through the tropical Atlantic and Lesser Antilles that impacted a wider area across the Caribbean Sea. These are red trajectories and they took 2 years. So you can see that under the assumptions of 1% windage and looking specifically at 2011 entry into the Caribbean and tracing this, you can see that there's clearly a path from the North Atlantic into the Caribbean, especially in that year. Now, next slide, please. This time series will demonstrate that. Now, to demonstrate the interannual variability of these pathways, the percentage of synthetic particles released across the Caribbean Sea in April through July of a given year that were backtracked to the North Atlantic, north of 23 north, within 6 months, 1 year, and 2 years is shown. A, the upper plot, using the HICOM surface currents and 1% windage from the same NSEP 10-meter winds was applied to it. And the lower panel, using the HICOM surface currents only with no windage. Note the change in scale of the vertical axis. So in other words, the whole time series with no windage fits underneath 1.5% of particles in the upper panel. So the most telling thing, well, let's see, these results show not only the dramatic increase in North Atlantic input to the Caribbean overall when windage is taken into consideration, that was one important result, but also the effect of the NAO wind anomaly in increasing the number of particles that arrived in the Caribbean from the north in 2011. So in other words, the anomaly was in 2010, early 2010, and by the time the particles arrived into the Caribbean, it was 2011, springtime actually, just in time for the massive amounts that surprised that nobody, the mystery of Sargassum suddenly showing up in the Caribbean in spring of 2011. So this shows that not only does windage make a big difference, but which supports our theory that Sargassum is subject to windage. Oh, and I should point out that it's not just a theory, really. There are a number of papers that demonstrate that Sargassum over the many years has beached itself, come up on shore in large quantities in places like Bermuda and in the Caribbean and all, in response to strong onshore winds. So we know that Sargassum is subject to windage, and we've simply tried to simulate it by using a 1% factor of real winds as simulated by the NSEP reanalysis. So this showed two things: the importance of windage and the importance of the 2011 arrival in the Caribbean, all supported by the HICOM model. Next slide, please. All right, well, this is the last part of the story. Once the Sargassum arrived in the tropical Atlantic, how were subsequent inundations sustained? This is a picture that shows various areas of of what we've been talking about, the West Africa region in green, the Amazon River plume in magenta, the east-west currents of the central tropical Atlantic, Caribbean Sea, and the Gulf Stream, and the Sargasso Sea basically in the reddish-orange there. Now, one hypothesis that was put out in the paper Wang et al. 2019, a year before our paper came out, and they actually, Xuanmin and Min Q are actually co-authors on our paper also, which added quite a bit of expertise and knowledge on the subject to our paper. Their hypothesis was that, this is a quote, the bloom of 2011 might be a result of Amazon River discharge in previous years, but recent increases in interannual variability after 2011 appear to be driven by two things, upwelling off West Africa during boreal winter, and by Amazon River discharge during spring and summer, indicating a possible regime shift and raising the possibility that recurrent blooms in the tropical Atlantic and Caribbean Sea may become the new norm. So the river plume hypothesis about how the nutrients, why the sargassum was blooming and doing so well in the tropics, it was mostly assumed to be caused by the nutrients from these on-land sources. Next slide, please. But then we have another hypothesis that I hope we've been able to somewhat prove. I will in the next few slides, I think. What fuels the recurrence of the blooms and what determines their seasonality? Our hypothesis is that our results actually show that sargassum patches aggregate in windrows along the ITCZ, the Intertropical Convergence Zone. Patches and windrows are exposed to high sunlight and open ocean upward flux of nutrients due to eddy and wind-driven mixing in the central tropical Atlantic. In other words, it's not all based on just the land sources and river plumes. There are abundant nutrients under the mixed layer, and this can be looked at in more detail. During the northern spring and summer, the sargassum drifts north with the ITCZ because it's a convergent system of the winds. So it forms a long windrow along the ITCZ, and large portions are adducted into the eastern Caribbean Sea during spring and summer when that's the flow direction, when the retroflexion of the North Brazil Current is not formed and sending the flow back over to the east. If wind mixing is strong and the mix layer is deeper than about 50 or 60 meters in the southern tropical Atlantic, the sargassum will bloom and form a massive windrow. Next slide. This is just a little sort of sketch based on data of these things. This is seasonal dynamics, the monthly average from 2010 to 2018. The sargassum density is shown as the multicolored pixels with the color bars on the right-hand side. It shows the location of the ITCZ, and you can see that the sargassum on the average aligns itself very nicely along the location of the ITCZ. The blue contours are the region of the highest amount of Ekman pumping, bringing nutrients up, and the northward excursion of the ITCZ is just indicated by the arrow. Seasonally, it moves to the north in the springtime, and then back to the south again. And yeah, the pink areas are just regions where there is some non-zero sargassum, but the higher amounts, of course, are all lined up with the ITCZ. This is a picture from July monthly average. Next slide. All right, now this is very interesting because the analysis also explains the interannual variability also of the sargassum into the Caribbean and surroundings. The monthly mean sargassum density is shown for the month of July from 2011 to 2018 in these panels. The Great Atlantic Sargassum Belt, the term was first used by Wang et al. 2019, is observed in all years, as you can see, starting in 2011. It wasn't in existence before then, all the way through 2018. It was absent in 2013, and it was delayed in 2016. We'll see in the next couple of slides. but other than that, it was present in all years, and it definitely is very severe right now in the tropical Atlantic and in the Caribbean Sea and regions downstream from there. Next slide, please. Yes, this one's a little bit complicated, but it's in the paper if you want to look it up later and take a closer look. Mixed layer and nutrient dynamics. The most intense sargassum blooms, shown as a time series from 2010 to 2018 as the brown line. The most intense sargassum blooms were observed when the deepest mixed layer depth, the blue line, and that is caused by the strongest trade winds, were observed. See, the mixed layer depth that is above zero means it's deeper than the climatology, and below zero means it's shallower than the climatology. When the mixed layer depth remained shallow relative to the climatology during October to December in 2012 and 2015, the bloom the following year was absent, as in 2013, or smaller and delayed, as in 2016. The mixed layer depth was shallower than normal for several months in 2012 to 2013 before a minimum of sargassum was observed in 2013. So there is a reason contained within these time series that explains both the absence in 2013 of a bloom due to lack of nutrients because the mixed layer depth was too shallow to reach down into the nutricline, past the nutricline, and in 2016 that it was just kind of neutral, but it caused a delayed and weaker sargassum bloom. Next slide. All right, to sum up that last part about nutrient inputs and mixed layer dynamics, our results show that in the tropical Atlantic, sargassum has diverse nutrient inputs, including upward nutrient flux driven by eddy diffusion, upward entrainment of nutrients as the mixed layer deepens seasonally, seasonal contact with the Amazon River plume, and positive Ekman pumping, open ocean upwelling, due to the wind stress curl. And that's just a beautiful photograph of sargassum over there. Okay, next slide. So to sum up the whole picture, our results explain the unprecedented spread and accumulation of vegetative biomass in the tropical Atlantic through the long-distance dispersal of sargassum from the North Atlantic. LDD, long-distance dispersal, is something that has been recently looked at with other organisms and larval distributions and fish and plant life, different kinds of algae. It's kind of something that's kind of recently been focused on in the literature. It's quite interesting. The extreme 2009-2010 winter NAO wind anomaly triggered a biosphere tipping point that caused important ocean-scale ecosystem changes in the tropical Atlantic with significant recurrent social and economic consequences, mostly negative, of course, as it piles up on the beaches. Tipping points are also getting quite a bit of attention in the literature in recent years, where some anomaly causes a tipping point, but that then pushes it over into a new regime situation. And that seems to be what has happened because sargassum was not known to have been in the tropical Atlantic previously, and now it's there and seems to like it and flourish. So we have to continue to look at and think about this. A new persistent tropical sargassum population is now established, supported by wind convergence aggregation, surface currents, and mixed layer dynamics in the equatorial and tropical Atlantic. Next slide. And then, of course, many concerns have to do with the predictability because in order to deal with it, resorts, beach places in the islands and tourist areas need to use all kinds of techniques to get it off the beaches because people do not like piles of sargassum rotting on the beach when they go to their resorts. And so they need to know when to get the bulldozers available or what are safe ways to remove it, etc. So how long will the present tropical Atlantic Caribbean episode last? Will it become a permanent regime or a new baseline? The answer depends on whether sufficient sargassum standing stock remains after each season to reaggregate and bloom again. This depends on possible flushing and residence times, wind mixing, and nutrient supply mechanisms in the region. Perhaps several years, such as the 2013 nutrient limitation event related to shallow mixed layer depth conditions, can return the sargassum distribution to pre-2010 conditions and end the present nuisance sargassum blooms. Sustained monitoring is required to understand the phenomenon better and assess any possible trends. And I think I'm at the final slide now. Next slide. And the future work, next step, is to think about the South Florida beaches. First of all, you can see the schematic. It was in the paper. It just sums up the various components of the story, how the sargassum got out of the Sargasso Sea, what happened to it then. An average of the sargassum from satellite is shown as the sort of goldish thing, and the loop current, note that, in the Gulf of Mexico. And this red star here is the South Florida beaches. Now, on the right-hand side here, we have two lovely photographs, courtesy of Valentina, from Crandon Park Beach on June 10th, 2020, just last week, just before the beaches opened up again during the pandemic for tourists. And you can see that at Crandon Beach, at least, it was covered with sargassum. And so that kind of has inspired us to look into, can we predict this kind of thing too? I understand that the sargassum is also piled high in Miami Beach and up in Broward County beaches also. So future work will extend the analysis to examine the processes that lead to sporadic sargassum inundations on the tourist beaches of South Florida. The working hypothesis, this is just something that it seems as if from a physical oceanography perspective, it's probably true, it's what I'm going to start with anyway, is that when sargassum is present in the Western Caribbean, and it is right now, it's piling up on the Yucatan, the Mexican Yucatan beaches where all the tourist spots are there too. It's a big problem right now. So when sargassum is present in the Western Caribbean, a short or young loop current, which is where the loop current goes straight from Yucatan to South Florida without having an excursion up into the Gulf of Mexico. A short or young loop current allows it to bypass the Gulf of Mexico and arrive offshore of South Florida, which normally it might stay in the current and go back to the Sargasso Sea. That is one route that sargassum can take. But if you have strong onshore wind events, it can all be brought onto the coast. And so I just was going to take a look at, the data exists to look at all components of this process, from satellite estimates of sargassum to the wind data to altimeter-based index of the loop current formation and how young or old it is. And so we could fairly easily see if we can make a prediction, a predictability thing for these events, because it's less usual to have the sargassum pile up on the South Florida beaches. It happens unexpectedly and suddenly. It doesn't last forever, but it would be nice to be able to see if the preconditions are all met each time it has happened. And so that, I guess, would be a logical next step on this whole thing. So final slide, please. Thank you for your attention. And if anyone has any questions, I'd be happy to make an attempt to answer them. I guess you have to unmute yourself if you have a question, right? Well, I, for one, can't hear anything. Manellis, can you? Oh, I might have, yes.
Maybe I think just give folks a minute.
Yeah.
I'm looking through the chat to see if there's any questions, and that'll give folks a chance to think about their questions.
Yeah, I think that my speaker might also be muted, but I can't see how to get rid of these windows associated with GoToMeeting in order to fix that problem. So maybe you could tell me if there's a question.
Definitely.
I'm on the phone here.
I don't see any questions.
Oh, actually, I should be able to hear everything on this phone, right?
Yeah.
Okay, well, that's good then. I see that it's time for us to quit. Anyway, at 3:45.
There's a question. Matthew asked if he thinks that climate change might be involved in this regime shift.
Well, to the extent that it is connected with the severity and the frequency and everything of the NAO, then that would possibly say why we had such an extreme event of the NAO. I mean, we've had negative NAO periods of time in the past, and that never actually brought sargassum down to the tropical Atlantic. This was the only time it escaped its usual place, but I'm sure that there is a connection, and it could be looked at by the modelers and climate experts. If Matthew has a comment on that it might be, I'd be very interested in hearing it. Do you have any thoughts? I'm not hearing anything.
Well, hi Libby, great talk.
Oh, here.
Thanks.
Hi, thank you.
Well, that'd be a great study to lead, but we need to design proper modeling tools to do that. Sankey might be interested also.
Oh, good. That would be wonderful, because as you know, of course, PHOD is getting more and more into sort of ecosystem. In addition to their wonderful climate work, we are also very interested in the connection between physical oceanography and ecosystems in the ocean. So that would be a nice study to look at from modeling perspective. Are there any other questions?
So Rick had a question, but you addressed it about whether the NAO was so strong and if that was related to climate change, but it sounds like there's interest in pursuing this from several of the scientists in the division.
Oh, good. And that way then the sargassum could be just used as a cool little thing that happened that everybody's heard of, and then, you know, look what this event did, and then go back farther and really explain, is it possible that we're going to get more of these? We are only really aware of this one seeding event of sargassum to the tropics, and it really happened in the past, because anecdotally none of the residents of the Caribbean or anyone has reported on this or mentioned it, but it could happen more in the future, I suppose. So that would be good to know.
Sounds good. And Sankey chimed in that he was interested. He said, good point, but he's having technical problems with his audio. There's a question from John Walter, who wants to know if sargassum is affected by water chemistry changes that are theorized to be occurring with climate change.
Well, that would also be a very good question. I don't know if any of my co-authors who are biologists are listening in. Probably not. We can certainly discuss that and look into it some more. I don't know. Cisco, are you still there? He's a fisheries person. He might.
I'm here.
Oh, hi there. How are you doing? Do you have a comment on John Walter's question?
With regard to water chemistry, I'm not sure if the question is perhaps on acidification or things. I don't think so. But like you said, it's a good thing to look at. We didn't consider that right now.
Right, and also you're more of a physical oceanography type anyway, I suppose, aren't you? Also, although right. Your title is fisheries now, but so yeah, but that would be interesting to look into. Some of the people who've been studying this for years would probably have thoughts on it. So, are there any other questions?
I think Claudia was asking about sensitivity to temperature or salinity.
Right, I think that sargassum and its blooming is quite sensitive to the temperature. I believe that it needs a range. I'm not sure what the numbers are, but if it's too cold, as it is out north of the Sargasso Sea, if it's too cold or too warm, as most plants react to that, it's out of its comfort zone and doesn't bloom as well. My patio gardenia doesn't like apparently any temperature zone. So, but anyway, yes, that will be an issue. And I'm not sure about the salinity thing in sargassum. Probably some people have done studies. There are various papers out about looking at growth rates of sargassum. They use tanks, both on land in the laboratory and out at sea, and study the growth rate. It's actually got a phenomenally fast growth rate when it's in the right conditions. That's why these blooms can get so out of control, I imagine. Any other questions?
There is one recent question that just got posted by Laura Carrillo. That was, is there a similar anomaly occurring in the Pacific to the one that is noted in the Atlantic?
I don't believe so, because I think that most of the world's pelagic sargassum, there are lots of kinds of species of sargassum, but the two or three species of sargassum that are fully pelagic for their entire existence, I believe are only found in any quantity in the Atlantic Ocean. But anyone who knows more about this could correct me. So I think that it doesn't happen there. And in terms of this study, the Sargassum just provided a very nice sort of tracer of circulation and an ability to look at the wind influence and the ocean currents and things, just like you must have heard years ago about the, I think it was Adidas sneakers, a tanker coming over the Pacific, lost its whole shipment of sneakers, and they started washing up on all the beaches from Canada down in California. And also people have traced the tsunami debris from Japan all the way across the Pacific too. So although it hasn't happened with sargassum, these types of things do happen occasionally and can be used as tracers. Are there any other questions?
So Gustavo just posted that they've cleaned Crandon Beach from large amounts of sargassum over the past 35 years, if I'm understanding the statement, since I've seen the park. And he's wondering if this is a different type of sargassum than what maybe is connected to the Caribbean sourced.
Yeah, I wouldn't imagine that before 2011, what was coming up there was, well, it certainly wasn't due to the same phenomenon that we've been talking about here. But yes, there is a certain amount. There is another sort of classic loop of sargassum that tends to go from the Sargasso Sea. Some of it can come through the passages to the northern Caribbean and get its way into the Gulf of Mexico, where it is found there also, and sometimes causes problems on the beaches of Texas, for example, during the right wind conditions and current conditions. But I imagine that these large piles have not been seen often in Crandon Beach, and these are almost undoubtedly caused by the fact that the sargassum, it's a huge year for it. First, they recognized it from satellite in the tropical Atlantic. Earlier this spring, it arrived at all the Caribbean islands. Recent weeks, it has arrived at the Yucatan and been talked about there. And now it's here in Miami, Florida. And we know that the loop current was short-circuited last week. And I still have yet to really delve into the winds and currents. It may have something also to do with the onshore-offshore location of the Florida current off of the beaches too. It might be that you need to have an inshore Florida current to get it closer, and then an onshore wind. So I'd be happy to discuss it with anybody who has thoughts about this. It sounds like a kind of a interesting little project to see if we could put that all together into a reasonable story.
So
Gustavo, do you have any comments about your question? I don't hear anything. All right, Renelis, is that it then from the chat box?
There's one last question, but maybe I should let folks that need to go ahead and go, and then the discussion can continue online. But I will tell you the question that just came in from John Walter was, I have noticed new sargassum colonies growing in several areas of Florida Bay, the Keys and Biscayne Bay. And he wants to know, how long does sargassum stay anchored and how long is it in its drifting phase?
Okay. Well, the kinds that we're talking about, I'll try to say the Greek names. I don't know if I'll pronounce them correctly.